Yes, it is. My nose is already very Italian. And on that camera with that, you got it from last term.
Perfect.
It's just huge. It's just, yeah. I'm proud of your Italian nose. So, let me back this thing down a little bit. Oh, man, I can't center it, though, can I?
Sure you can.
I can insert it.
If you minimize the window, Sean?
What's that?
If you minimize the window?
Yeah, you can move the window.
Oh, God. Let me try. Yeah, oh, I see what you're saying, Michael. I see what you're saying. I see what you're saying, and then I can kind of switch. I was going to insert a row. This is much easier. Thank you.
You're welcome.
I think this will get the job done-ish. I think this will get the job done-ish. So what I've done here is I've generated kind of a fictitious population of 6 random numbers. And if you press, this is like your project number 3 from 243. If you press F9 a bunch of times, you'll see updates on those numbers. They're changing every time I press F9. And they're very, very simple. They're just random numbers between 0 and 1, rounded off to 2 decimal places. So it's the same kind of thing you were doing back in the day in that project at 243 where you were rolling dice, pulling burritos out of Taco Bell bags, or whatever else, iPod randomizing, all that wonderful Monte Carlo stuff. And that's cool. But this is a population, right? So this is 6 numbers of which you can't get all 6. So think of it like the card thing we did yesterday. Deck of cards, you're pulling cards out of the deck, looking at them, marking what you got, and then resampling again. You can't look at the entire deck because there's too many of them to look at. So this population's a bit fictitious in that it's so small we actually can see them all. But it's going to prove a point that's going to generalize out. Okay, now down here I've got a few parameter measures for that population. I got mu, aka the
Average.
very nice, the average of the population. I got MED, aka the median. Let's do a quick review of 243. What's the average of the population? What is the average of a data set? Good. Add them all up, divide by how many there are. Good. What kind of words do you think of when you think of average of a data set? What kind of, besides that, which is great, tell me your name too. Natalie, thank you. I love that. Add them all up and divide by. Why do we do that? Do you remember from 243 why you add up and divide by? What does it ensure that every element of the population then has? What's it? They all have the same thing. What this says is, these 6 data points, are 6 distinct data points. If you had 6 data points that all had the exact same value, that would be the value they would all have to come up with the same total result of data in the set. I did this in 243 with lollipops on that one day. I gave you all a bunch of lollipops and I said, what's the average number of pops? And by the way, you can't add them up and divide by 10. And you kind of stood there looking at me like, what the hell's wrong with you, dude? And then eventually you figured out, oh, if I give the person with 1 a couple, and I give up some of mine, and by the end of the day we all had 3, then the average number of lollipops was 3, and that's kind of the sharing measure. We all have the same amount. So, averages are great. They can also be misleading. How well is 0.4 representing these 6 things? We'll talk more about that in this class extensively over and over again. Because sometimes averages aren't good for data set description, right? Like in what cases? When is an average not the best way to describe a data set? Go, Ben.
When you have extreme outliers.
Nice, extreme outliers. Because what happens with extreme outliers? They chase the outlier. The average chases the outliers, those extremes. Sometimes you get lucky and they bounce. But if they don't, the outlier is going to get pulled. That's why I have to be very careful looking at your guys' exam grades. Because you guys generate skewed exam results. Yay, that's a good thing. You skew in the good direction. They look like this, where you got F and A. So even if a 1 or 2 low grades are here, the average gets yarded down towards that outlier. So you gotta be careful. We'll talk about that more in this class. Median. Tell me about the median. Tell me all about him. Geographical middle, exact center, good. I like that. So if we took these 6 values and put them in order, was it 0.14, 0.22, 0.25, I guess 0.44, 0.48, and 0.86. We'd go between 3 and 4 and average those 2, and that's what your median would be. Good. Can you see this? It would be more obvious. It's little sigma. Little sigma. What does he tell us? Good. That's your deviation in the population. What do you remember about that? Deviation, standard deviation in general, whether it's population or sample. What do you remember about it?
65% exists within 1 standard deviation.
Nice.
And 95% exists within 2 standard deviations.
Good. With one caveat. I love that. With one caveat, and only if we know that The data is shaped like a bell.
Okay.
But yeah, but we have been dealing with that so much, and we will continue to deal with it in this class, that it's okay to assume that one. Yeah, absolutely, absolutely. Good. What is it in general? What can you give me an idea about standard deviation that applies even if the data is not bell-shaped? What is it a measure of? What are you measuring?
Error.
Good, good. And wait, go more with that, Karen, if you don't mind.
So you have to, when you take a sample or you take an average, you have to have some error on either side, right or left of your average.
That's good. So you got an average, but the average is 40, or 0.4, excuse me, 0.4 in this data set. Well, none of these values are 0.4. You got a 0.48, 0.25, 0.86. All of them are off of the average somewhere. So what is that number really telling you?
What your possibility is of less or
Yes,
more.
it's your average offness, if that makes sense. If you measure all the offnesses of all the data points, that's the average of the offness. We used to call it the average distance from average back in the day. And I know it upsets you guys at first because you're like, you just said average twice. I did, but there's two averages at work here. There's the static average of the data set, and then the distances from that average each data point has. That's what you're actually averaging, is those distances. Yes, good. Sigma squared. He's a goofball. He's called the variance. We didn't talk about him hardly at all in 243. I don't know how much Donna talked about it in 243. He's not really important until now, like today, and then the remainder of the term, but he'll kind of be in the background, or she. It'll be in the background. It can be gender specific. It's this, thusly. This is a weird one here too. It's the proportion of the data set that's greater than a half. I just decided I wanted to work a fraction in here somehow. So I picked a random proportion bigger than a half, because we're going to be using a half today later on with the experiment. And I said, what proportion of the data are larger than 0.5? Okay, and right now it's at 0.17, which is 1/6, because there's only one of them. 0.86 is bigger than 1/2. The other ones are not, so 1 out of 6 is about 17%. Every time you press F9, you'll see that reload. The average deviation. Oh, please, Ashley.
The portion larger than half. Could we compare that to like the 50th percentile?
Yeah, exactly. Well, yeah. Let's see. Yes and no. Yes, in that when you take the data set and split it up into percentiles, the 0.86 will definitely be above that. The other 5 will be below that. But essentially, these guys all have their own percentile. There's 6 of them. Percentiles usually dealt with sample data, but that's cool. We can apply it to here too. So here you'd have the 1/6 percentile-ish, the 2/6 percentile, the 50th percentile would be the median. Would actually be that guy. So it is and it isn't. All it is, it's actually much simpler than that. I'm just looking at the data. Here, let me hit F9 and reload it for you again. Look at something a little bit more interesting. There we go. Now it's a third. The percentage bigger than a half is now a third, because 3 of the 5 data points are bigger than 0.5. That one. Oh no, excuse me, 2 of 2/6 is 1/3. So that one and that one. Yeah, don't trust my arithmetic ever. You hear that out there in YouTube land? Try doing it. So 1/3, 0.33. So that's all we're measuring. Very, very simple. Very, very simple. And we like this because we're going to be testing this kind of stuff in this class. Average deviation is another measure of standard deviation that we mentioned but didn't talk a whole lot about in 243. You'll find out why today. The mode, with a small data set like this, you might not have one because there's only 6 data points. You might not get a repeater. The range, remember what the range is? We briefly spoke of this, and you guys actually, in my class at least, you guys discovered it yourselves.
Oh, biggest and smallest.
Right, it's the distance from the biggest to the smallest. So it's 0.84 in this case because you go from 0.03 to 0.87. There's your 0.84.
And then mode is the value that's most often. Is that
Yes,
right?
exactly.
Okay.
Your modal value occurs the most frequently,
Right,
but
okay.
with 6 data points randomly selected, you usually don't have one.
Right.
Because there's not enough. And you're generating basically 100 different values.
I'm just making sure I remember.
Absolutely, you got it. It's been a whole week. Lots gets flushed out. Skewness. Skewness is another cool measure. That measures how off of a bell curve you are. Or actually, take that back. Minus. It's how off of symmetric that you are. You don't have to be a bell curve, although bell curves are symmetric. So it measures how far away from symmetry you are. When it's positive, like this is, I believe, I'm going to go by memory here, positively skewed means your average is to the right of your median. I think this is right. And negatively skewed means the opposite.
Yeah.
Right. So it actually, I'm getting a visual in my mind, and I always screw this up, because positively skewed makes you want to think that it's leaning this way, but it's actually leaning this way because the average is what makes it positively skewed. Those of you that know this pretty well, am I saying this correctly? I always just say skew. If it's off of 0, it's skewed. It's skewed. And there's measures for skewness that I had you guys play with in 243. But don't worry if you don't remember those. Oh, Chris, go ahead.
Is skewness the same thing as offness?
Well, I like the word offness. It's offness from symmetry. So I like calling it offness. So it's deviation from symmetry. Of course, the question always is, how deviant can you be until you go, it's not symmetric anymore? Because a deviation, say, of 0.01, if the skew is 0.01, is not that skewed. So you could say that's still arguably a bell-shaped curve. But when you start getting into skew, we had measurements for this in 243, when you start getting skewed exceptionally to one way or the other. There's cutoffs, and we can talk about it if you want to, but it's not that important for what you're about to see right now. Now, the reason I started with a small data set is because in each of these 9 graphs, what you're actually seeing is all possible samples of size 2 taken from each of these 6 values. So in other words, this average, this correlates to this little box over here. Median correlates to this little box here. Mode, mode's actually down here. Skew, why did I do this order? Standard deviation, variance, average deviation, proportion, and range. Now it's a little much to look at, but here's what I want you to think about. These blue dots at the top of each one, the blue dots at the top of each one are the values of that statistic in each possible sample drawn of size 2. So in other words, if you drew 2 elements from this, say you drew 0.03 and 0.07, that was the 2 elements you drew. The average of that would be 0.05. And 0.05 is one of these blue dots up here. It's going to be over here somewhere, one of these small ones. See what I'm getting at there, friends? If you grabbed 0.87 and 0.31 and average it, that's going to be 118. So that's going to be somewhere right around 0.56, which is going to be one of these blue dots over here. So what you're actually seeing is every single possible sample average drawn from this population. With me so far? There's a lot of them. There's a lot of them. There's going to be 36. I think I did it with replacement. So it'll be 36 of them, 6 times 6. So one of the samples might be 0.67 and 0.67 with replacement, rather than 30, which you do without replacement, or rather than, you see what I'm getting at there, kind of? So you see a lot of sample averages. Here's all the possible sample medians. There's a lot of repetition, which is why you're not seeing as many points. Modes, the variances are down there. Standard deviations are all here. Skewness is all here. Average deviations, proportions, and ranges. They're all lined out. These are all possible. This took a while to set up. All possible samples of size 2 drawn from that population of 6. Now, when you do statistics, this is one thing you have to keep in mind, and we talked about this in 243 very briefly in the last week of class. I'm sure it's been flushed from your memory, and that's okay. When you do statistics on a sample, you don't get all of those. How many do you usually get? Go ahead, be brave. When you do a study on a sample set of data, you get 1. Exactly. You get 1. You get 1 of those. I mean, we had this discussion in the very last week when I had you guys draw up those beautiful curves on the board at the end of that activity. And I said, yeah, that's a beautiful bell curve. And the highest part of that bell curve is right over mu, and we're happy. But then I said, but the problem is that even though it's over mu and we're happy, you only get 1 of those. What if you end up getting this one? Or what if you end up getting that one? We'll deal with that. We have dealt with it. We'll deal with it continually in this class. So I just want to make sure you know when I press F9 and those blue dots keep changing, that's what you're actually looking at. That's what you're looking at, is all of those beautiful values over and over and over again. Is that okay? Okay. Now, in each graph as well, there is a red square and a green triangle, if they exist in the data set. If they exist in the data set. Sometimes they don't. So the red square is the average of all of those sample statistic values. So that red square is the average of all those blue diamonds up top. This red square is the average of all those blue medians up top. This red square is the average of all those blue modes, and so forth and so on and so forth and so on. So you got 9 averages of all those sample statistics. It's fun. It's fun to set. It took a while to set up, but it was fun to set up. And then the little green triangle, the little green guy at the bottom, he's equal to the population parameter that's over here. So right now, the mu, the population average is 0.47, and the little green triangle is at 0.47. So it's a lot to look at. But do you kind of understand what other pieces are? Yes-ish, getting there. Okay, good. I'm going to kill the lights for this part, because I really want you to see, why did Sean put 3 of them in yellow and the other 6 in white? So I'm going to hit F9 a few times, and you guys watch and see if you can tell me, why I colored those 3 yellow, and the other 6, I should say, white. In other words, those 3 that are yellow are special in some way. In what way? In what way are they special? What's happening in those 3 that's not happening in the other 6?
The averages keep
Gary Price, tell me that again.
The averages keep repeating.
Oh, look. For example, look at the top. Wait, leave the pointer. Don't. Hot damn. Look at the average chart up here. Focus on the average of the sample averages, the red square, and the green triangle under it, which is mu. What happens to the red square and the green triangle? What's going on, friends?
They're moving together.
Oh, they're moving together. They're moving together. Take a look over here at the variance. There's the average of all the variances. Here's the population variance, sigma squared. What's happening with them? Hot damn, they're moving together. Take a look down here at the proportion. Now, I threw some letters in here. You can barely see them. It says WLOG, that's without loss of generality. I've used those letters in 243 with you too. What that means is, I used the proportion of a half here. I could have used anything. I could have used a third, I could have used a sixth, I could have used 2/3. I just used a half because we use it so often in this class. So, without loss of generality, I could test any proportion. Why am I using this? I'm standing right here. I could have used any proportion value that I wanted to, but I just used a half. Watch the square and the triangle in that one. What's going on, friends?
Following.
Hot damn, it's following. What's it not doing in the other 6 on average?
Not following.
There's always a little bit of a gap on average. There's a little bit of a gap modally, and this guy, the mode only shows up occasionally over here, because sometimes there's not a mode. Okay, you've got some deviations here, over here the skew, the average deviation, here's the range down here. So there are only 3 measures that, on average, target the parameters that you're actually trying to target. Because here's the deal with the class is called statistics, right? The class is called statistics. What do we really want to know? We'll say it again.
Statistics 2.
Well, that's right, the second one. Part the 2. Part the 2. But what do we really want to know about in this class? Do we care about statistics, or do we care about the what that they're representing? The population measure, which we call, also starts with a P. Oh, it's a word we don't use very much because the class is called statistics. Parameters. It's the parametric values. We care about the parameters. We want to know on average how much is blood circulation increased if we tell second stroke patients to start taking 2 aspirin a day. We want to know that kind of a thing. We want to know, on average, what range of motion increase do we have with a hot tub therapy in geriatric patients. We want to know that. We want to know how ADD is affected with a certain set of regimen in attention span measurement tests. We want to know those kinds of things. But we can't know the parameter values of those things. So we draw a sample, and we measure the sample. And then we infer from the sample information. And there are only 3 statistics that accurately target, on average, the parameters that we're going for. The average, the proportion, and the population variance. Everything else misses on average. Everything else misses on it. That's not to say they're useless. There's tools around the missingness. But this course here deals with these 3, and in particular 2 of them. We'll get to that momentarily too. So that's why I didn't give a whole bunch of hooting about average deviation back in 243, because it doesn't do a very good job. Standard deviation actually on average does a slightly better job, but it's not as good as the variance. But don't worry, we have tools for that as well, which we'll get to. So this is a lot to look at. Hell yeah, it's a lot to look at. But it also implies why we do what we do on the data sets that we have. So I'm going to shut this bad boy down. I'm going to fire this bad boy up. I'll have this PowerPoint posted for you guys at some point later on today, so you don't have to write this stuff down if you don't want to. Plus, it might be kind of a headache to look at right now. Those three statistics that I just mentioned, the average, the proportion, and the variance, have a special name in statistics. They're called unbiased estimators up there on the concrete. Unbiased estimators. And what they are is they are statistics that on average target the parameter that you want to know something about. So, X bar, your sample average, on average targets mu, which is what you care about. You care about mu. You care about the average range of motion in that geriatric patient. You care about the average blood flow for an aspirin, a 2 aspirin a day second stroke victim. You care about these things, but you can't get them. So you get this. And from that, you infer something about this, which is kind of what this course is all about, is that inference. How do we get from here to here? That's for continuous data, or for averaging data. What about discrete data? Yay us. That's what this guy down here is all about. Proportions. Now, here's a new symbol. And we're going to keep using them through the course of today and the course of the course. P hat. P hat. I had a bunch of nursing students a few years back love this. Every time I say P hat, these chuckles. And finally, now 3 weeks later, what the hell are you guys laughing at? And they're nursing students, they actually have these things they call P hats. Little plastic things that look like a little pilgrim's hat that you put in the toilet and you pee into. So they made me one with P hats written all over it. Maybe every time I said it in class, I had to put the damn hat on. I've since burned it. It's gone. But anyway, P hat is your sample proportion. What you want to know is your population proportion. Does that look familiar, little p? Does that look familiar to you guys from 243? Yeah. It should, because we were using it in 243. But in 243, we were dealing with parameter values. On your last exam in 243, not to bring up bad memories, but 1/2 of...
Yeah, sorry. I did so bad.
1/2, but you did so well with everything else in all balances, which is why I designed my grading system the way I do. That's why I designed it the way I do. Why I designed it the way I do. But 1/2 of 1% of children have peanut allergies. 1/2 of 1% of children have peanut. That little p is 0.005. Now the reason they can call that a parameter is because they've measured so many kids. They're essentially calling it a census. And if they've got it, if they're calling it a census, you can get away with calling that a parameter. But we're not going to get away with that in this class because we're not going to have that luxury of time, resources, and everything else. We're going to have to start from a sample data set and get a proportion from that data set, which we're going to call p hat. Which is it's basically x bar for proportions. And p bar was already taken, unfortunately, somewhere else. So they gave it a little, they gave it a chevron instead. P hat. And last but not least, little s, we were calling that back in 243 who? What was little s? Go ahead, be brave.
Standard deviation.
Exactly, your sample standard deviation. Just like little sigma was your population standard deviation. But squaring it gives you the variance. When you're calculating it by hand, you guys in my 243 calculated one standard deviation by hand. I believe it was Ernie.
Yeah.
Bert and Ernie, you did Ernie by hand. And then we stopped doing stuff by hand because that got annoying after a while, especially with large data sets. You actually calculated this first and then took the square root of it to get the standard deviation. So you actually had done a variance in class manually once and then we never did it again, which is fine. But we stopped talking about the variance. Does anybody remember why? This is a really, really obscure question. Does anybody remember why we didn't talk about variance so much in 243? It's okay if you don't remember this. It wasn't drilled into your head like other things were. It had nothing to do with statistics. Units. It's the unit on the variance. For example, suppose averages go with standard deviations. They're paired up, as Karen eloquently said earlier, how off you are. So an average has a unit. Suppose it's milligrams per deciliter. Whatever, milligrams per deciliter. So it's the concentration of something in the bloodstream. A standard deviation will have the exact same unit, milligrams per deciliter. But when you square it, it's now milligrams squared over deciliter squared. I don't know what the hell that is. What's a squared milligram? I don't know what that is. So we kind of ignored this contextually in 243 because it didn't make any sense. But now we got to deal with it because now we've got the fact that it's an unbiased estimator. However, with your permission, I'd like to not deal with it because the amount of time it takes to deal with it in this class is prohibitive with 10 weeks. Okay. So we're going to focus just on 2. We're going to focus on averaging and we're going to focus on proportions. Chris, give me your concern. Go ahead.
Why'd you bring it up?
Because it's one of the it's out there. I'd be remiss if I didn't talk about it a little bit. So we're going to talk about these guys here are the biggies. These guys are the biggies, and I like keeping it simple. Your textbook has this in it. I don't want you to look at that. I'm steering you away from those sections. But you've got averages, which are essentially continuous data, modeling and measuring, and you've got discrete data down here, which is basically in proportions. Or it's basically in proportions and versus averages. Fair enough? We're going to start today with proportions, and what I kind of have the course do is flip-flop back and forth from proportion to average, You kind of learn each thing both ways and compare and contrast, which works pretty well. So here's the problem. Here's the problem, as you might remember from that Excel spreadsheet that was just up there on the board a few minutes ago. So yeah, we were very happy, for example, with the average. Because in the average of averages chased very predictably the parameter, the mu, the parametric average. But the problem, of course, is how many of those averages themselves are actually coming close to that square. So how many of those blue squares are you going to get with your study, usually?
1.
You're going to get 1. You're going to get 1. You're not going to get all of them that you can then average together. I say usually because studies are often replicated, and we're going to talk about this a lot in this class. When you get replicated studies, then you get more of these, and you start getting clusters around where, hopefully, the true value that you're looking for lives. So you might get a cluster of 5 studies that goes, bop, 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 and then you're like, oh, okay, that's better for me to work with than just that by itself. And we'll deal with that in this class. It's one of the many things we'll deal with in this class. But here's the problem. At first, you get 1 study, which means you get 1 of those blue diamonds, which means you've got what's called sampling error. Now, this is not a bad kind of error. This is the error Karen was talking about before, when she said that standard deviation measure is basically a measure of error. It's not bad. It's just offness. I mean, not to use that word again, Chris, so I just did, didn't I, damn it? But that's what it is. I mean, you're not going to hit the parameter perfectly on average. You're going to be off a little bit from it. So how do we fix that? How do we fix that? Think about the word error and how we use that back in 243. I wouldn't say often, but I'd say more than once or twice. Somebody just said it.
As a margin of error.
You apply a margin of error onto it. That's exactly right.
Yay.
So what you do, Christina, beautiful, you have your center, which is your X bar in this case, and then you apply an ish. I like to call them wings too, because they kind of look that way when you actually slap them out. And I know in 243, as Michael pointed out, if you go 1 standard deviation, you get 66. If you go 2, you get 95. We generally stick with 2 in here. And we call the entire margin of error 2 standard deviations. That's our modal go. Because that's usually what industry uses. A p-value of 5%, 95% confidence. So rather than saying it's 2 standard deviations, we just call it a margin of error. So what you do is, basically, you stretch out a margin of error around that statistic. Why is this good? Why is this a good idea to do this? What happens to the parameter now? Now, I know you won't know what the parameter actually is. But where is the parameter now?
Within your...
Say that again, Mary. That's loud.
Within your margin of error.
It's within the margin of error. And here's where the 95% comes in. 95% of the time, if you do a sample study, you're going to trap the parameter in this interval that you've created. Now, there are going to be some values that are too far out. They're going to be missed. But on average, you're not going to miss the parameter. You're going to hit it 95% of the time. I had a whole project devoted to that because I think textbooks don't do a good enough job really nailing that idea down. So I'll have you guys do an F9 Monte Carlo stuff to really nail that idea down as to what it means to trap a parameter 95% of the time. It probably means nothing to you right now, and I don't think it should. Right now, it's 9 o'clock in the morning. You're not quite caffeinated enough. That's totally fine. But it will make a lot of sense in this class as we go. It has to, because that's kind of the basis of the entire thing. Okay. Let's state the question again for those playing the home game. So the question is, if you spin a penny and let it fall, what's the chance you get heads? And so far we've got a couple votes. We've got 1 and 3 because it seems right. We've got 1 and 2 because why would it be anything different than flipping a coin, catching it, and putting it in your hand? We've got to vote for 1 and 3 because there are 3 outcomes, technically. There's heads, tails, and edge. The trick with that, Richard, is what? When you're assuming what? Yes, Mayor. You're assuming that every one of those possibilities has the same chance. Well, but then you can't call it 1 in 3. You can say that there are 3 outcomes, but you have to take a weighted average of those 3 outcomes. So you can't call it 1 in 3. You have to say it's 1 out of something, and that something is determined by weighting it properly. Fair enough? Absolutely. But I agree. 3 outcomes. Maybe even more. Maybe like diagonal would be a possibility too, with a very, very small likelihood.
Yeah, because the weight of one side of the penny versus the weight of the other side of the penny will change what's going to happen.
So a vote for, since if you look at the penny on both sides, this is why I wanted to recall the wheat penny if anybody had one. If you look at the 2 sides of the penny, you say, oh wow, there's different pictures on both sides. I wonder if that will influence the spinning. Because that won't kick in necessarily if you flip a coin and catch it and put it on your hand, because you're interrupting it. But maybe there's some physics that's happening that is hard to quantify, as Richard pointed out. It's hard to quantify it. But maybe it's still in action there. So the question I have really is, how are we going to determine the answer to that question?
Yeah.
Love it. We're going to take a sample. Now, here's the problem. It's a sample, correct? It's a sample, which means we're going to have some error involved in it, right? Little errors. So here's the basic process, friends. Ah, crap. Of course, that one is right on top of the... Well, I'll read it to you. Hopefully the screen's fixed for Tuesday. I'm thinking it will be. Here is the basic principle of what we're going to do for the first, I'd say, 3 weeks of the course. Maybe 3 weeks of the course. I'm going to give you a big course overview today, where the course is going to head from now till day 20. So what you're going to try to do in the first couple weeks is, you're trying to estimate a parameter, a parametric value, mu, little p, one of those 2 in this class. Either little p, which is the proportion, in this case proportion, percent. Oh, Susie asked a great question. I kept saying proportion, and she's like, I don't remember you saying proportion in 243 all that much. And she's right, I didn't. For some reason, when things shift to inferential stat, even though it's the same idea you've been playing with ever since 243, instead of calling it a probability, like we did in the binomial, it just shifts to sometimes being called a percentage or a proportion. For whatever reason. So, when we talk about the percentage or probability of spinning heads, it's the same as the proportion of heads that you get when you spin a penny. Same exact words, 3 different P words all mean the same thing. So, what you're going to do is, you're going to form what's called a confidence interval, which I tend to shorthand CI because it's easier to write. You've already seen one. You've seen a bunch in 243 already. We weren't calling them that, though. Whenever you saw a poll that I made you read over and over again that had a percentage and then a margin of error, that was a confidence interval. On one of those exams, I said the chance of, I forget what we were studying on that one exam, was at least blah or at most blah, and you guys took the percentage and added and subtracted a percentage to it. That was a confidence interval. That's what that was. You were giving a range of values. So in other words, when I ask you what's the chance of spinning heads on a penny, you're not going to say it's 1/3 or 1/2 or 5/6 or 99%. You're going to say it's a certain percentage plus or minus a certain percentage. Because as Ashley just pointed out, how are we going to figure out these percentages? We're going to start with a sample. That's what step 1 says. Unfortunately, it's kind of hard to see. It says start with a random sample. I'll have this PowerPoint up for you later on today. You don't have to write this down if you don't want to. It'll all be linked off the schedule page. So number 1 is start with the random sample. Start with a random sample. Always start there. Number 2 is find the center. Find the middle of that random sample. And in our class, it's only going to be one of 2 things. Either a percentage, proportion, probability, which will start today, or an average, which will start, I'm thinking, like Thursday of next week. So it's going to be one of those 2 things. That's the only thing we're going to mess with in 244. That's it. That's all. That's all. There's lots of other things we can center our intervals on, and you'll deal with them maybe in later classes. But in this class, if we can get it dialed for these 2, then we're happy. We're happy we can make this work. And that's great, except it's not all. It's not the be-all and end-all, because you remember from that last image that your center, that little blue diamond that you get, might not be right near the parameter you're looking for. So how do we adjust it? How do we adjust it? You slap the margin. Well, more trials. Good. That's actually good, Richard. More and more trials, as a function of which you'll see later on today, more and more trials actually do a great job of minimizing that. But you can never get it to 0. So you have to put your margin of error on there, which I sometimes just call the wings. You're going to put the wings on that. So you have a center value, and then you're going to say, let's put some wings or a margin of error on there, which is tied, and again, this board's in the way, but here it says, remember mu plus or minus 2 sigma? Mike, you brought it up earlier today. Mu plus or minus 2 sigma, that's your margin of error stretching out to both sides. That's going to take care of any uncertainty, or at least 95% of the uncertainty out of our sample. So yes, we start with a random sample, clearly, absolutely. So here's what I want you guys to do, and we may have to stretch out through the building to do this, because I'm looking at your desks, and your desks are tilted, and I think that might be a problem. So let's do this. You guys may have to stretch out. I want you to take your penny, find a flat surface to spin it on. Okay, when I say spin, you may have to practice this for a while. No, seriously, people always say that. I don't know how to spin a coin. It's okay. I do it with 2 hands. I've seen some people do it with 1. They flick it. I don't think it matters as long as it gets spinning. So you just kind of grab it and then let it do that. And then let it fall. Let it keep going until it falls down. And then mark what you get, heads or tails.
How many times, Sean?
Do it 10 times each. Very good question. Do it 10 times each. You may have to go out in the hallway and find a flat surface. That's totally fine. But go do it 10 times. The floor, be careful with the floor. Make sure there's no ribs in the floor that are going to interrupt the spinning. But go have at it. Spin them 10 times and see what you get. That's still centered-ish. It's not bad. I still see that. Get a little bit closer in. It's not bad. You say that again? I did this. I didn't do it. I didn't do it on 243 last term, but I did a exam review in 244, and this actually worked as long as it was like half the screen on the camera. It was actually visible, which surprised me. I didn't think it would be. So let's collect our data. I'm going to start a distribution up here for us. You flipped out a 10, or you spun 10 times.
Yeah.
So the number of heads you could get anywhere from 0 to 10, essentially. So let's just go around the room and collect the data, and then we'll analyze it in the TI. We'll make a histogram because we like those. Maybe do a box plot because we kind of like those too. Just get an idea of shape, get an idea of what we're looking at. Anybody get no heads at all? All tails? Over there. How about a 1 head out of the 10? We got 1. We got Jess. Just got 1. 2 heads out of 10. 1, 2, 3. Okay, beautiful. 3 heads. 1, 2, 3, 4, 5, 6, 7. 4 heads out of 10. I wish I had done this too. I forgot to do my own. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Love it. 5 heads, half and half, which is one of the predictions, right? One of the predictions was 1/3. One of the predictions was a half. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. How about 6 heads? 6 heads. 1, 2, 3, 4, 5, 6. You were just putting that on the wall, right? As you weren't voting.
No, she wasn't.
She wasn't voting.
No, yeah.
I have a project now.
Well, good for you. I mean, I guess good for you. 7 heads. 1, 2, 3, 4. Actually, no, 3. 8 heads. 9 and 10. Okay, there's our distribution, friends. There's our distribution. And we like distributions. We do. Distributions are great. We can do statistics on distributions. We can run averages. We can get standard deviations, and I love all that stuff. But in order to analyze this better, I think we should take a look at it. It looks bellish to me. It looks bellish just based on the values of the numbers, but I want to make sure that I'm not inventing something that may or may not actually be bellish. So let us look. Let's get this bad boy into L1 and L2. Say again. It looks it, but the thing is, I'm going on the length of the numbers of 1 versus 2 digits, and I want to get an idea of the relative size of the 7 and the 3 and all that, and kind of see. I want to make sure that I'm getting that curvature that I think is there in my mind is actually there. I'm tempted to agree with you, Jamie. I think it is too. So let's see, L1. I'm going to clear that out.
What are we doing? What program?
We're not doing a program at all. We're stripping it back to basics.
Okay.
That's a great question. I gave my 243s a bunch of programs last term. Gave you a bunch. 2 of which you used, maybe even 3 of which you used. There was dist fill, which was fantastic. There was dist draw, which we didn't use all that much of. And then there was the normal. We won't be using dist fill all that much anymore, and here's why. Dist fill was really used an awful lot when you had an entire population behavior, like a binomial, where you knew that the proportion was a certain amount. Here, we're asking the question, what is the proportion of heads when you spin a penny? So we don't know what that is, so we can't set a distribution up. So we're going to go back to old school and be entering stuff in L1 and L2. You can use dist fill. If you have dist fill, you can use it a little bit. I'll show you how if you have dist fill. So if you want to use the program, you don't have to do this, but if you want to use the program, I have to change my battery soon. You go to dist fill, and I can give anybody that doesn't have this program if you want it. And then smallest x to largest x would be 0 to 10. And then when it goes to here, we were usually doing binomial, but we don't know what the parameter. This is binomial. Can you see why this is binomial?
Yeah.
Give me a couple reasons. Number one,
It can be measured.
we're going heads or tails, either or. Even though we admittedly could have a third edge, it's never happened in almost 15 years of doing this experiment. So I'm going to rule it out as it can't happen in this experiment. So basically I have two experiments. Set sample is huge, right? Go do this 10 times. Set sample, independent, fixed number of trials, 2 outcomes. Mwah! That was beautiful. That was absolutely beautiful. So this is binomial. It's just that we don't know what those independent trial probabilities are. But it is binomial, even if we don't know that. But that's what the point of this problem is to figure out what that independent probability is. Nice. So what you can just do is then go to manual. And then it says done, and then you can go back in and edit it, and then you can put in L2. So it might not be worth your time to do this. It might just be just to go 0, 1 through 10. So we got 0, 1, 3, 7, 11, 12, 6, 3, and then a bunch of zeros. Fantastic. All right. What should we do first to analyze this data? Oh, I heard two things. I heard graph and find the average. Can we do it in that order? I like that order because that way we know how much to trust the average. If we've got a lot of skew, we might want to be critical of the average. So, Ashley, what's on your mind?
I was going to say 1 by 10.
Yes, that's I think what Carrie's saying too, is find it. Let's run the graph first, just because I like doing histograms. I had you guys do quite a few of them back in 243. Let's get a histogram, make sure this bell shape that I'm seeing in my mind is actually there, not just in my mind. So, second, y equals, this is where I think this is really going to help. So you guys are at home and you're like, how do I make a histogram on a TI? I can talk through it, which I think this is, of course I'm wasting time by talking. So second y equals, number 1, plot 1, turner on. Yeah, histogram is good. X list. What is X list again?
Your frequency.
That's actually your Y list,
Sorry.
or they're actually calling it free. X list is just your data. In this case, the variable, they're calling it X being a random variable. The variable you're interested in is how many times you got heads in 10 trials. That's the variable of interest here. That's what your first column is. Your Y list, or your frequency, is going to be L2. Make sure you put that in there. Make sure you put that in there. Otherwise, it's going to graph 0 through 10, all with a frequency of 1, which doesn't look like what happened at all. Cool. Cool. Now, the easiest way to get to a graph, do you remember? Well, graph would work assuming your window's set up properly.
Yeah.
Zoom 9, Terry Price. Zoom 9 gets you a histogram. It might not be the most perfect histogram, but it gets you a histogram that fits your data. Now, we often finagled this once we got to this point in class. My favorite finagle is going to the window button and finagle an X scale. So I'm going to finagle X scale. I'm going to make that, instead of 1.66666, I'm going to make it 1. Because it doesn't make a whole lot of sense to have 1.66666 other than, with like Motorhead. But it makes more sense to have it 1 because our data goes by 1. 0, 1, 2, 3, 4. Starts at 0. I like that. The part that's a little confusing is you probably want to change Xmax to what? Oh, Xmax, not you're thinking Y, Susie. We'll get to that in a second. X is your data. What's your biggest data value? 10. You actually have to put it at 11 because the bar has to stretch a set distance to one side. So in other words, in order to have 10 bars, you have to have 11 spots to put the 10 bars in. We'll see that in a minute. Now, Susie brought up we may have to also adjust our Y max depending, but I'm just going to hit graph at this point and see what it looks like. And that looks pretty darn nice, actually. Except for the fact there's no labels. But here's your 0. There's no heads, 1 head, 2 heads, 3, 4, 5, 6, 7, 8, 9, and 10. This is X is number of heads. X is number of heads. Like that very much. Like that very much. And here's your frequency up here. Here's your frequency. Again, not labeled, but that's okay. We can live without labels, I think, because we have the actual distribution directly over there. Cool? What was I trying to get you guys in the habit of back in 243 of always slapping up with the histogram? You got it, a little box plot, box and whisker. I'm going to turn a second plot on too, although I think we're safe. This is really well-behaved data, actually. Slight skew. Somebody had Chris asked about skew earlier today. It's got a slight left skew. Slight left skew, but it's ish bellish. I mean, it's definitely got a nice bell component to it. We'll talk about ways of measuring normality in this class. It's part of this class. So I'm going to go back to second y equals. Chris, go ahead.
You said left skew, so that means it's a negative skew?
That would be a negative skew because the average is getting pulled this way a little bit from symmetry. And don't worry about that. I just like to use the word skew.
Yeah.
It's skew. I think I told you the story before. When I ask a statistician, well, how do you keep left skew and right skewed straight? They often tell me, well, just think about where the curve is leaning. I'm like, oh, good, yeah. And then think the opposite.
Yeah.
Great. As if statistics doesn't confuse students enough. Think what you're thinking, and then think exactly the opposite. But only for this thing. Anyway. So plot 2, turn. Oh, God. I should have changed batteries before I came here. I just lost my batteries. Hang on.
You can use mine for the class.
Can I plug it in?
83 and
It's
newer.
I got a solution. Hang tight. I got to turn this.
I have a plugger.
I can pull batteries, and then you guys can't. Is batteries okay? You don't mind, Jared? Oh, I appreciate it. They don't usually. That was weird. Yes, let's. If you don't mind.
I don't think it was that weird.
No, it was because I didn't get a warning last class. I used it. Usually, I get a warning, then I go back to the office to change the batteries. Oh, these got corroded. What the hell? But I used them yesterday. Thank you. Make sure you return these back. All right. Jared Spreader, saving the day. Thank you. That's just the corrosion. There we go. Thank you so much. All right, so now, okay, we're back. Thank you so much, Jared. This is wonderful. So, turn a second plot on. So second y equals plot 2. Let's turn that bad boy on. So we're going to set this up identical to plot 1, except the choice. We're going to go with modified box plot, which mine's already set to from last time we did it.
Oh, wait, I got lost. Second what now?
Second y equals, just like the previous
Okay.
one.
I know, but I had to get help.
That's okay. Second y equals, and everything's the same. L1, L2. It's asking you to pick an outlier. It should already be set that way from last class. And then just grab your modified box plot, which is this guy right here.
I'm not having that look like this. What is wrong?
And then just hit graph, and you'll see your box plot on top of your data.
Well, I did second y equals, but I think that's where I get stuck.
There you go.
Wait, but what did you put?
I just turned it on. You're golden.
Okay, but I don't know what, I think I don't know what.
And then you just select it from there.
Oh,
By pressing
and then
enter.
you push in. Okay.
So, I'm feeling pretty good. I don't see the presence of any goofy outliers that are pulling my average anyway. I do see a nice bell-shaped data. I see this. What does this tell me here, friends?
Q1 and
Very nice. There's your quartiles. Tells you where your middle 50% of your data is. You can trace it if you want to. So it looks like the 25th percentile is 3, Gesundheit. The median is 4. The 75th percentile of the third quartile is 5. Go ahead, Carrie.
Isn't that just one standard deviation?
It's not. Not necessarily. It can be that the standard deviations are not tied to box plots. Thank you for asking that, by the way. Standard deviations are tied to averages. So it's the average distance from center in a sample. Box plots are based on relative position. So in other words, when I see that the first quartile is at 3, that means 25% of the data is below 3. When I see the median is 4, that means half of the data is below 4, half of the data is above 4. And when I see the third quartile is 5, that means that 75% of the spins came up with 5 or fewer heads, and the other 25% came up with more than 5 heads. So it really doesn't tie to standard deviation as much as relative position. Is that fair? Great question, by the way, great question. So now, based on this, let's do what Ashley and Carrie asked me to do originally, which was run one of our stacks. We know what some of them is already, what some of them are. We know the median is 4. But let's run one of our stats to get the average, because I'm feeling pretty safe about using an average in this case. I'm feeling pretty safe. No, not a crazy amount of skew. No goofy outliers. So I'm feeling pretty happy about this. Jared, do you want to run this? Or
Go for it.
You good? Okay.
I'll mess it up.
No, we do. So I'm going to run one of our stats. So I'm set. Remember this for playing the home game. Playing the home game. Stacked calc. I'm going to erase this. We don't need this anymore. One of our stats. And the one thing I want to be careful about, L1, L2. Is L1, L2. Is L1, L2. So second 1 gets you L1, comma. Second 2 gets you L2. Enter, get you the goodness. Enter, get you the goodness. So, here's what happened. We're averaging about 4.4 heads per 10 spins. We're averaging about 4.4 heads. Looks like 43 of you ran the experiment. 43. So I'm going to keep track of that over here. Our sample size is actually 430 because we have 430 individual spins, 10 at a time, 43 people. That is 430 trials, if you will, even though you guys are doing it to 10 at a time. This number right here, which I know we ignored quite a bit, I know we ignored this quite a bit back in 243, that's actually how many heads you guys all got in those 430 spins. So I'm going to put that over here. That's 189. So here's the penny spin results. Penny spin results. Penny spin results. Out of 430, let me try something. I'll see if this works. You guys can let me know if you watch this. Oh God, that might not be visible at all. Out of 430 trials, you had 189 successes. In this case, success is getting heads on a spin. Okay, so here's my question. With this in hand, and with this in hand, you've also got a standard deviation of about 1.4, okay, which can't be ignored. That's part of this, actually. How would you answer the original question of what is the probability of spinning heads? So we had original votes, right? We had 1/3, we had 1/2, we had 1/3 again, but based on a different logic. So what do you think? What do we say? Well, how do we answer this?
4 out of 10.
About 4 out of 10, maybe 4.4 out of 10-ish. We're gonna go that way. So what would that be? That'd be 44%. Yeah. About 4.4 out of 10. About 44%. Okay, I love that answer. I think it's a great answer. Here's a question I have for y'all. Suppose I give you the pennies back, so you still have most of them, and I say, okay, do the experiment again. Spin it 10 times again. Let's recalculate our results. What's going to happen then? We're going to get 430 trials again.
Yeah.
But then what's going to happen with X? It's going to change. Did somebody say ish? Did somebody say ish? I thought I heard ish. Maybe I just want to hear ish. It's going to change, but is it going to change far from that?
No.
Probably not. I'm guessing probably not, unless what just happened was some kind of freaky outlier event. Okay? Probably not. So, and then if we run it again, we'll get 430 more trials, and you'll get a different value of X most likely, but close to this. So can we just say it's a 44%? Can we say 44%?
Basically half.
Oh, it's basically half. So we're saying if we apply an ish to the 44%, then essentially what we can do is say we can't prove that it's not a half. I like that. Let's go with that. Let's go with that. So what we're going to use today, in the interest of time and your interest, let's use technology to get the answer of the ish, to figure out what the ish is. And then on Tuesday when we come back, we're going to uber analyze where that margin of error came from. Mathematically. We're going to break it down mathematically. But let's go to the TIs right now and show you the shortcut that gets you that margin of error, that ish that we need. And I'll come back with your permission, because I'm looking at the clock. I don't want to bore you guys with mathematics right now. We're getting towards the end. I want to kind of keep the statistics rolling. We'll start class on Tuesday with an analysis of where these numbers came from, if that's okay with you guys. Please, Jamie.
Is this the number 2 part?
The number 2 part.
Oh, statistics.
Oh, no. Actually, number 2 part, it will give us number 2 and number 3. So, Jamie asked a very good question. She asked, when you think about put this on the board over here. When you think about that number 1 and 2 and number 3, what we're doing right now is we are estimating a population proportion. And we're going to call that little p, with a confidence interval. Spelled that right, yeah. Interval built around little p hat. Little p hat, p chevron, p hat. Oh, p hat. So what we need to do is we got to do steps 1, 2, and 3 as we're up on the PowerPoint originally. So step one is get a good random sample of binomial discrete data. And we just did that. So we're done step 1. So get a good random sample of binomial discrete data. Binomial and discrete be binomial. Whatever order you want to use. The commutativity of adjectives. We got that. And the data that we have says we have 189 heads out of 430 trials. Okay. The next part from that PowerPoint earlier was find the center. Find the center of your sample. Well, the center is essentially the center of where that bell curve was that we just saw. It's the center of that beautiful histogram. But that histogram is frequency counts. So what we're going to do is we're going to put the center of that frequency count into proportion form. So that's where we're going to calculate p hat. The center of the data set we're going to call p hat. Okay? P hat is going to be defined to be, and this is the binomial distribution kicking back here. You're going to take, or even simpler, basic probability. Number of successes over the number of trials. I mean, if you think about the very beginning analysis of probability from 243, that's what we did. We got an event space, and we got a sample space, and we divided them. That's why it's 50-50 when you flip a coin. That's why it's 50-50 when you flip a coin, because it's 1 in 2. There are 2 possibilities, heads and tails. One of them is heads. They're equally likely. The trick with this one is we don't know about the likelihoods. We can't make the assumption. Things like dice and coins and pulling cards out of a deck, they're easy to analyze because they are equally likely. Not so much with reality like this. So, for us, for our data, what does that end up being? Our p hat for our penny spins. For our penny spin, or excuse me, p hat of heads is going to be 189 out of 430, which ends up being what? About-ish? Give me, you don't want 2 decimals? 0.44. Oh, right. Duh. 44 divided by 10. Exactly. 0.44. Now, we know that we can't just say it's 44%. The question was, what's the chance that we get heads on a coin flip, or a coin spin? We can't say it's 44% because that was our sample. In our sample, 44% of our sample came up with that. But if we did it again, we get a slightly different value. In the population, it's going to be a different value on top of that. So what we have to do is we have to apply the margin of error. That's what step 3 is. So now we have to apply the margin.
Because the more trials you run, the more those 7 or 8, 9, and 10 are going to build in. That's going to bring
Nice, Chris. So as we run, Chris is remembering this from 243. As you do more and more trials, and we're about to see a whole lot of trials up on Excel. I have data from about 3 years worth of doing this, all compiled together. What happens is the intervals get very tight because, as you remember from 243, central limit theorem says as you sample more and more and more, the curves bring in and get nice and tall around that average nice data. Remember that. Awesome. In, up. Good. So we've got to apply the margin of error to p hat. What that is going to look like, friends, is p hat plus or minus this margin of error. I can't treat this margin of error correctly with the amount of time we have left today. So with your permission, what I'd like to do is calculate it using the technological shortcut today. and then analyze it on Tuesday and show you what the hell's going on with it. Because it's slick, and it's cool, and it's tied back to the binomial, just like this is. But I can't do it justice in 10 minutes, and I'm not about to just ram it in 10 minutes. So sorry, try to keep it PG, kids. So let's use, sorry, Carrie. Let's use technology to get this margin of error, okay? Let's use it. So grab your TIs. Stat menu. We spend a lot of time in 243 in the edit and calc screens. In 244, we're going to spend a lot of time in the test screens. A lot of time over there in tests. Now this is a little bit cryptic, and we'll talk more about why. We'll talk more about why it's called this and why it's cryptic on Tuesday. Go down until you find the command that's called oneprop zint. It's down a ways.
Zint.
There it is. Mine's an A. Oneprop zint. Oneprop zint. We're going to give you a kind of a quick technological introduction here. We're going to analyze this in detail on Tuesday. I promise you this. Grab that one. Grab that. You have to input 3 things to this. X and N are the obvious ones. So we're going to input 189 for X. We're going to input 430 for N. And that's fantastic. There's one thing, good night, Michelle. One thing's a little bit goofy. This thing called C level. That's confidence level. Now, in your gut, how confident would you want to be? 100%. Absolutely. You cannot be 100% confident. We'll talk more about why on Tuesday. I promise you this. Leave it at 95. Unless it's not 95, just type in 95.
Mine says 0.95.
That's okay. Either 0.95 or 95, it'll accept either one. That's totally fine. This is called 95% confidence. I'll give you a quick introduction as to what this means. This means if you run this experiment that I just had you guys do 100 times. So in other words, spin the coin 10 times. Then do that again 99 times. So you end up with a whole bunch of coin spins. On average, 95 of what we're about to create are actually going to answer that question correctly. More on that on Tuesday. That's a lot to wrap your head around. And more on Tuesday. More on Tuesday. For right now, let's just calculate.
Just enter.
Just hit enter. Well, then I'll calculate and hit enter. Okay? So, what this gives you is p hat. There's p hat right there. Notice our 0.44% is what Mary told me. And it gives you this beautiful range up here. That range of values is the 95% confidence interval with its margin of error already attached to it. So in other words, see how this p hat plus or minus e is down here? P hat is about that 0.44. But once you apply the proper margin of error to it, the minus the margin of error brings you down to 0.39, and adding the margin of error brings you up to about 0.49. So you're sitting on roughly a 5% margin of error. Roughly a 5% margin of error, essentially. So when you see the 95%, I'm going to put this over here so you can actually see it on the video. The 95% confidence interval for the percentage of time you get heads. The 95% confidence interval, and I know that phrase is not making a whole lot of sense right now. I know that. But what you're going to get used to saying in this class, starting Tuesday, is I'm 95% confident. Can't be 100. I'm 95% confident that when I spin a penny, it's going to land heads up at least 39% of the time, but no more than about 49% of the time. That's the kind of answer you have to give. You can't say it's 44%, or it's 1 in 3, or it's 1 in 2. What you have to give it is a range of values based on your data. You have to be able to give that range of values because there's sampling error built into your data. That's the problem with data, is that it's got sampling error. You didn't get the population's values, you drew a sample from the population. So here's a question, though. I want to ask this question. This is a fun question. There were 2 numbers thrown out at the beginning of class when I asked this question. What's the chance of heads? 1 in 3 and 1 in 2. Can we discount either of those now based on our sample data? We can discount both of them. 1 in 3 is too small. It's outside this interval. and 1 and 2 is too big. It's outside this interval. See the power of this? Remember, what you want to know is what little p is. You want to know what little p is. Hold that thought, Christian. Give me a minute. I love this question. Hold on. We want to know what little p is. All we know is we're 95% sure that little p is somewhere in this interval, which means we're 95% sure it's not 1/3. We're 95% sure it's not 1/2. Go, Christian, please.
If we calculated for tails instead of heads, would we get the same number?
We get the reciprocal. We get the complementary values, right? 0.51 up to point whatever the complement of that is. Because it's binomial. It has to be the flip-flop.
It'd be like 56.
Exactly. It would be the flip-flop of that, wouldn't it?
Okay.
Which would disprove the 1/3 and 1/2. Instead, it would be 2/3 and 1/2.
Right.
Great question. Great question. I want to analyze this more carefully on Tuesday. Chris, go.
But that's only based on 430 trials.
No. Love this. Love this.
But
No. This is great. We had to accept how much of a margin of error on this?
5%.
5%. That is not usable in most cases. Industry standard, 3% margin of error at 95% confidence, which means the only way we could get this published is if we got it down to 3% margin of error. Well, how can we do that? More trials. I don't have time to do it justice right now. I've got thousands of trials on record from this experiment. We'll take a look at it on Monday or Tuesday because that will explain also why we should not feel bad about just these 430s. Yeah, if you guys don't mind dropping the pennies up here, maybe on the screen. There was one more question. Jamie, go. Yes. No less than 39%, but no more than 49%.